Welcome back to the Algebra 2 series, and today we're looking at three brief examples dealing with the ellipse. First example here shows the statement that we're to find the length of the minor axis. Of course, we know that the length of the minor axis comes out to be twice b, so that's what we're looking for. And they give us vertices at 7, 1, and 7, negative 7. So let's put 7, 1 about here, 7, negative 7 down about here, which tells me that the full length of the major axis is 8, or putting the center here at 7, negative 3. So that's the first step, that we have that value. And of course, if this is a vertex and that's the center, then we have an a value of 4. The other thing we know is that the focus, one of the foci, is at 0, so that tells us that c is equal to 3. So this problem turns out to be pretty simple if we write out our Pythagorean identity for the ellipse a squared equals b squared plus c squared. Substituting the numbers we know, this is 4 squared equals b squared plus 3 squared, or 9, so that's 16 minus 9, or 7, is b squared. B therefore is radical 7, and so the length, we're looking for the length of the minor axis is 2 radical 7. So very quickly we can find that solution. Let's move on to the second problem. Find the endpoints of the minor axis for the ellipse having these vertices, negative 1, 3, and 11, 3. So we're way out here somewhere. And again, this problem shows that here at 5, 3, we must have our center in order for us to have 6 units both ways. So A equals 6 to get us to the vertex out here. Once we found A, we also realize that this is a horizontal ellipse, or x minus h squared over a squared, y minus k squared over the b squared equals 1. So of course we've got this little mystery going on because they've given us a point 8 comma, and this is around 5, so about 8, and up here at 15 halves. 8 comma 15 halves, and we wonder what is that used for? But that looks like a substitution point, x, y, in our equation. Let's see if we can use that to find what we're looking for. Again, we're looking for the endpoints of the minor axis, and therefore we're looking for the b value. We've already found h, so that's going to be x minus 5. That comes from the center of our ellipse. We also know a squared is going to be 36 because a is 6. The y minus the k value of 3, and over b squared equals 1. And here's where we don't know the value of b, but by substituting in our point 8 comma 15 halves, so I could put an 8 right there, and I can put a 15 halves right here, and I should be able to solve for the b value in this equation. Let's see if we can do it. In the first case, 8 minus 5 is 3 squared, or 9 over 36, and I'll bring that down to 1/4 in just a minute. 15 halves minus 3, and that's 6 halves, so that becomes 9 halves squared over b squared equals 1. Somewhat ugly, but that's okay. 4b squared is what we're going to multiply by, because remember 9 over 36 is 1/4. We'll try to cancel that out and multiply by all three terms here. We'll get b squared plus, in the second case, the b squared cancels, leaving us 4 times 9 halves squared, and that's equal to, that's an ugly equal sign, let me try that again, 4b squared. Continuing on, we see here that the b squared is going to be just fine the way it is. In the second case, the 4 cancels with the denominator 4, giving us just 81, and that's 4b squared. Or 81 equals 3b squared. Finishing this out, 27 is b squared, so b is 3 radical 3. All right, that takes care of business on that. We just have to figure out the endpoints of the minor axis. Of course, we're going from our center, and we're going to go down, and we're going to go up 3 radical 3 units. So the endpoints of the minor axis are going to be 5 comma 3 plus or minus 3 radical 3. Up and down 3 radical 3 from the center 5 comma 3. It takes care of business on that one. And let's go to our grand finale here. If an ellipse has equation, as you see here, then find the ordered pair for the endpoint of the lattice rectum located in the first quadrant. That is very confusing. So in this case, though, we know that this is a horizontal, so that must be A right there. And we must have B going up and down. So I'll make it a little smaller. We don't know exactly what the numbers are. So if we just sketch a little graph here, there's a picture. What we're trying to find is the endpoint of the lattice rectum, which be located on the end of the segment which goes right through a focus. And we do know this. C is the length from center out to the focus. So this must be, the ordered pair must be C comma, uh, and then whatever happens when we plug a C in there. So plug in a C and get an answer. And that's going to be our ordered pair. If the equation is x squared over a squared plus y squared over b squared equals 1, then really all we're doing is plugging a c in for x, so that would be c squared over a squared plus y squared over b squared equals 1. And we're solving for y. So in this case, I'm going to multiply through by a squared b squared. And I get this. C squared b squared plus a squared y squared equals a squared b squared. And I'm solving for what? Y. I'm solving for y. I remember that now. A squared y squared equals a squared b squared minus c squared b squared. Okay, I don't know where this is getting me, but let me just keep working this out for just a minute. First of all, I see that a squared y squared is equal to, on the right side, I'm going to pull the b squared out, and I'm going to get a squared minus c squared. That tells me something. That tells me something. Because when I started this whole thing, I remember there's a Pythagorean identity that said a squared is equal to b squared plus c squared in an ellipse. Therefore, a squared minus c squared should be equal to b squared, or I can replace that a squared minus c squared with another b squared. That'll give me a squared y squared is equal to b to the fourth, or y squared equals b to the fourth over a squared, giving me a final value of b squared over a. The y value, therefore, is b squared over a, for whatever c value you get. Well, let's put that up here then and show that that's kind of sweet. The endpoint of the lattice rectum, therefore, is going to be c comma, and of course you could write c as the square root of a squared minus b squared. That's one of the things that we could substitute for the c. If you didn't have a c to begin with, you could use the a and the b to find that. And then the y value is b squared over a. So that's a real nice way to figure out the actual ordered pair for the endpoint of a lattice rectum. And keep in mind that that's a plus or minus situation, because we could go up and down from there and find both of those. Well, I hope you've enjoyed these 3 examples and that they might help you in figuring out some of your problems with the ellipse.